my name is Jacob Farley, and this is my presentation on Lab 3 concerning orbits. So the purpose of this lab is to use a computational model in GlowScript to predict and display the motion of objects in orbit in space. So part 1 will display a star orbiting a black hole, and part 2 will display the orbit of a spaceship in a planet and moon system. Two separate models, computational models in GlowScript will be used for this. The fundamental principles and equations that we will be using are the four given here. Um, the first is to calculate FNet perp. The second is to calculate FNet parallel. The second is a velocity update formula, and the final is a position update formula. So we can derive all of these formulas using Newton's second law. And we also need to know that FNet is equal to FNet parallel plus FNet perpendicular, and that FNet perpendicular is equal to the centrifugal force, mass times velocity squared over r. And we also need the law of gravitation, which is F equals the gravitational constant times mass 1 times mass 2 over distance squared. So for part 1, we were asked to calculate the mass of a black hole given the initial conditions of the star's mass, a location at 0, 0, 0, and a seed trajectory that we were not shown. This code used to find mass of black hole as well as the net forces, perpendicular, parallel, and total. It was done using the equations on the previous slide. The calculation loop found the black hole to have a mass of about 1.1372 times 10 to the 34th kilograms, with its orbit shown in the picture on the right. So, as for interpreting this, we can see that the net force represents the gravitational pull of the black hole on the star at each moment. The rate of change of momentum shows how the star's motion is actually changing from moment to moment. The parallel component of the force determines the speed of the star, and the perpendicular force changes the direction of the star. So in part 2, we had to find the initial velocity of a ship so that it would have a unique orbit that is affected by both a planet and a moon, without crashing into either one of them in a 700-hour period. So we used the previous formulas in order to find approximate, or to use initial velocities that would be affected by both, and a lot of it was trial and error. So I ended up with the vector negative 24,000, 24,310, 0, as my meters per second. So it resulted in this. Unfortunately, I couldn't find a velocity to make the figure 8 shape requested, but I was able to make a very unique orbit with several different ellipses of all shapes and sizes that survived the 700 hours. So if the imaginary system in part 2 had a black hole and a star in addition to the planet and the moon, the computational model would need to include forces between all 5 objects, which gets very complicated very quickly. There would be a dominant force coming from the black hole because it had significantly more mass than all of the other objects, which means that it would have the greatest gravitational force given that they are not significantly further from one another. The next dominant would be the star, then the planet, then the moon. But really, it's all going to revolve around the black hole. So, possible errors, because it's purely computational, there really aren't any. It could only come from inputting incorrect numbers, using the wrong equations, or messing up the code. Because the equations and code were essentially given as a template and all the numbers worked out well, I think that it's very unlikely that there were any errors. Finally, we can conclude that we were able to find a relatively precise mass of the black hole and a plausible initial velocity for the spaceship between orbits without crashing for 700 hours. Thank you.